October 30th, 2025. 3. Atlas is now closer to the Sun than it will ever be again. It's perihelion, the point where its trajectory bends under the most extreme solar forces imaginable. For the last several weeks, the world's most advanced observatories have gone silent. The object is hidden behind the Sun's glare, unobservable from Earth, unreachable by most instruments. No one truly knows what's happening right now, only that this is the moment everything could change. In risk theory, there's a term for events like this, moments that sit outside every model, that no one predicts until it's too late. They call them black swans, events that reshape our understanding of what's possible. Financial markets, global systems, even planetary science, all have been blindsided by them before, but never one on a cosmic scale, because 3I Atlas isn't just another comet. It's the third confirmed interstellar visitor ever detected, and unlike the two before it, this one is massive, metallic, and highly reflective. Some measurements suggested unnatural symmetry in its rotation. Others showed chemical traces no known comet should contain. And now its enduring temperatures no material from interstellar space has ever survived. This is the moment of maximum uncertainty, the period when the data disappears, the sensors go blind, and physics is forced to make assumptions. If something unexpected happens now, a fragmentation, a flare, a signal, or a change in path, no one will see it until it's already over. So tonight, we ask a question that isn't just scientific, it's existential. Could 3I Atlas's perihelion, this silent, blinding moment behind the Sun, be the kind of event that history will one day define as a black swan? Because if so, we may already be living through it. To understand whether 3I Atlas's perihelion could trigger a black swan, we first need to understand what that term truly means, beyond finance, beyond metaphor, and into systems science. The phrase black swan was popularized by Nassim Nicholas Taleb to describe events that are both unpredictable and catastrophic, yet rationalized in hindsight as if they were inevitable. These are the moments that break models, expose assumptions, and force civilizations to rewrite their frameworks of understanding. A black swan has three conditions. First, it must be an outlier, something that falls far outside the realm of regular expectation. Second, its impact must be extreme, shifting the trajectory of systems or knowledge. And third, it must be explainable only after it occurs, when analysts and experts scramble to construct stories about why they should have seen it coming. For decades, black swan theory was confined to economics and social systems, the 2008 financial crash, the 2020 global pandemic, even the discovery of interstellar objects like Oumuamua. Each of these represented shocks that emerged from the blind spots of predictive models. But 3I Atlas occupies a category of its own, an astrophysical wildcard on a cosmic scale. Astronomy, for all its precision, is still bound by probability. Orbits are calculated, masses estimated, temperatures modelled. But the assumption underlying those calculations is that the observed object obeys familiar physics, that it behaves like things we've already seen. 3I Atlas has challenged that assumption from the start. Its composition, trajectory, and luminosity all fall outside normal distributions. Statistically, it shouldn't exist, at least not in the way it does. When scientists call something unprecedented, it usually means unexpected but explainable. 3I Atlas is neither. It doesn't fit the models. Its motion across the solar plane hints at subtle propulsion, or active venting that cannot be fully reconciled with gravitational or outgassing forces. The uncertainty surrounding its mass and albedo ratio pushes it beyond the category of a comet and into something undefined. And now, as it faces the most energetic phase of its solar encounter, that uncertainty compounds. If black swans are the rupture points where models fail, then this moment and the perihelion of a foreign interstellar object is a perfect stage. We have an event that cannot be fully observed, driven by forces we cannot yet measure, with potential outcomes that ripple far beyond astronomy. A fragment could alter solar particle flows, an electromagnetic surge could interfere with satellite calibration, even a data anomaly could shift public confidence in institutions that claim control over the unknown. What makes black swans so dangerous isn't their unpredictability, it's our dependence on predictability itself. Modern civilization is built on models of markets, weather, trajectories, energy outputs, risk projections. When something emerges that breaks those models, the shock isn't just physical, it's cognitive. Our systems panic not because the world changes, but because our understanding of it fails. Consider how previous cosmic surprises have unfolded. The Tunguska event of 1908, when a small asteroid exploded over Siberia, flattening 2,000 square kilometers of forest without warning. The Chelyabinsk meteor of 2013, brighter than the sun, injuring over 1,000 people, detected only after impact. Each of these moments forced the scientific community to acknowledge a gap in its predictive capability, yet both were minor compared to what an interstellar object might represent. 3I Atlas doesn't come from within the solar system. It carries with it the chemistry, structure, and motion of another star system entirely, perhaps even the remnants of a technological process alien to our understanding. To claim we can anticipate its behavior as it skims the solar corona is, at best, optimistic. At worst, it's hubris. That's the defining feature of black swans. They thrive in environments of overconfidence. The more we believe we understand reality, the more devastating the surprise when something contradicts it. Scientists today are confident that 3I Atlas will survive perihelion, bend its trajectory and move outward again, much like other interstellar visitors. But that confidence is built on assumptions, not direct observation. Right now, those assumptions are being tested under solar conditions no probe can monitor. The danger isn't necessarily that the object itself will cause harm. It's that it could reveal something about our limits. If 3I Atlas fragments in ways we can't predict, emits materials we can't classify, or alters solar readings that don't fit established models, it would force a paradigm shift in how we view interstellar objects. In other words, it would become a black swan for astrophysics, a single observation that rewrites everything. Black swans emerge when visibility is lowest and confidence is highest. We're in that exact window. The sun has erased our line of sight, the agencies have gone quiet, and yet public speculation grows louder by the hour. It's the same psychological pattern seen before every disruptive event in history, a calm surface masking hidden volatility. And that's what brings us to the core of this investigation. Because if 3I Atlas's perihelion represents a genuine black swan, then the conditions surrounding it, the silence, the data gaps, the improbable behaviour, are not coincidences, they are indicators. The next question then is timing. When does uncertainty peak, and why is this moment specifically so critical? Every celestial body that orbits the sun experiences a perihelion, the moment when it reaches its closest distance to our star. But in the case of 3I Atlas, that moment is far from routine. It's a narrow, high-stakes window in which everything we know about this object could change, and everything we don't know could finally reveal itself. For reference, 3I Atlas's perihelion occurs around October 30th, 2025, right now. Its estimated distance from the solar surface is roughly 0.38 astronomical units, placing it well within the region where solar radiation pressure, magnetic turbulence, and plasma density reach their most volatile balance. At this proximity, the sun's corona, extending millions of kilometers into space, is not an empty field of light, but a storm of charged particles, radiation, and magnetic filaments moving at hundreds of kilometers per second. Most comets, when they pass this close, behave predictably. They flare, shed material, and sometimes fragment. But 3I Atlas isn't like most comets. Its reflectivity, its mass distribution, and even its spectral signature have defied those expectations since its discovery. Spectroscopic data gathered weeks before conjunction revealed traces of nickel, cobalt, and possibly even complex carbon compounds that shouldn't exist in these ratios for a natural body. And now, exposed directly to the solar furnace, these materials could react in ways no model has yet simulated. The perihelion window isn't just a physical phase, it's an observational blackout. From Earth's perspective, 3I Atlas is lost behind the sun's glare. Even our most powerful instruments, the Hubble, the James Webb, the Very Large Telescope, are blind to it. Ground-based observers can't track it. Even space telescopes must wait until the object re-emerges. For now, only solar missions like NASA's Parker Solar Probe and ESA's Solar Orbiter could potentially glimpse it. But even those sensors face limitations when the target aligns directly with the sun's core brightness. That's the paradox. The moment of maximum scientific value is also the moment of minimum visibility. Every significant transformation, thermal cracking, structural failure, chemical emission, plasma discharge, would happen now unseen. We are effectively flying blind through the most critical part of this event. Historically, perihelion has been the great equalizer of comets. It's where fragile bodies disintegrate and resilient ones reveal their true nature. When Oumuamua passed perihelion in 2017, it accelerated unexpectedly, showing non-gravitational motion that led to years of debate. When comet Borisov reached its perihelion in 2019, it survived intact but displayed an unusual gas-to-dust ratio never before recorded. 3I Atlas sits somewhere between those cases, but with far more mass, higher velocity, and a composition that defies comparison. What's different now is that this perihelion doesn't just test the object's structure, it tests our observational infrastructure. Every sensor, every network, every algorithm we rely on to track interstellar phenomena is being challenged by something we can't currently see. It's like trying to study lightning while it strikes directly into the sun. Let's break down what could happen inside this window. As 3I Atlas approaches the solar boundary, it's subjected to thermal stress exceeding 1000 degrees Celsius on its surface. This alone could cause volatile materials trapped within the nucleus to sublimate explosively, producing powerful jets that alter its spin and trajectory. For a standard comet, this is ordinary behavior, but in an interstellar object with unknown internal structure, those jets could act more like thrusts than random vents. If the object's geometry allows for directional outgassing, something even slightly asymmetrical, it could result in a measurable change in acceleration, similar to what Oumuamua displayed after its own perihelion. That's the key concern: non-gravitational acceleration. It's been detected before, but never at this scale or proximity. If 3I Atlas experiences even a fraction of that, it would indicate internal dynamics, or mechanical processes, far more complex than natural sublimation. Then there's the magnetic factor. The solar magnetic field near perihelion isn't static. It's a living, shifting web of polarity changes and reconnection events. When a highly reflective, possibly metallic object passes through those lines, it could induce electric currents within itself, creating temporary electromagnetic fields. That could generate plasma interactions, visible as luminous flares or ionized trails, and potentially emit radio frequency anomalies. It's no coincidence that scientists are monitoring the sun for strange signals during this phase. If 3I Atlas possesses a dense metallic core, as some infrared readings suggest, it could even act as a transient conductor through the solar plasma, momentarily altering the flow of local magnetic lines. That would be unprecedented. It would also explain any unusual coronal disturbances or solar radio spikes observed in the coming hours. But perhaps the most important part of this window is psychological, not physical. The world is watching, but unable to see. It's a strange collective paralysis, scientists waiting for data, governments waiting for confirmation, and the public waiting for someone to say what happens next. Yet no one can, because no one knows. This is the textbook condition of a black swan: high uncertainty, high impact potential, and complete informational blindness. The question then becomes, what happens if something does occur in this blind spot? A solar flare triggered by unexpected plasma interaction, a sudden disappearance from predicted trajectory, even a temporary radio silence from solar probes at the exact time of closest approach. None of these outcomes would be individually catastrophic, but together they could redefine our perception of control, and when the object finally emerges on the other side of the sun, we won't be observing a continuation of its journey. We'll be confronting the unknown aftermath of an invisible event. It could appear exactly as predicted, slightly altered or entirely changed in behavior. Each scenario carries implications that ripple across astronomy, physics, and even public trust in scientific predictability. This is the moment we stand in now, the thin, brilliant edge of the unknown. The light we see from the sun hides the data that could rewrite our understanding of cosmic order. And as we wait for 3I Atlas to reappear, we face the same unsettling truth that has haunted every civilization confronted with the unexplained. The most important events in history are the ones we never see as they happen. For the first time since its discovery, 3I Atlas has vanished completely from observation. No telescope, no probe, no sensor on or around Earth can currently track its position. What we have now is not data, It's absence. And in astrophysics, absence is often more revealing than presence. The term solar conjunction describes the period when a celestial body passes behind the Sun relative to Earth's line of sight. During this interval, the Sun's glare overwhelms all optical detection systems, creating a temporary communication void. For deep space missions, it's routine. NASA suspends transmission with Mars orbiters for days at a time during conjunction to avoid data corruption. But in the case of 3I Atlas, this blackout isn't routine. It's the single most critical moment in its entire journey, and it's happening in silence. Before conjunction began, observatories worldwide tracked 3I Atlas with increasing precision. Infrared, optical, and radar measurements converged on a trajectory so exact that even minor deviations would be noticeable. Then, around October 25th, signals began to fade. By the 27th, optical visibility was gone. By the 29th, even the Solar and Heliospheric Observatory (SOHO) lost it entirely. The last confirmed data point was a faint infrared reading from the Parker Solar Probe, a thermal echo that lasted less than 2 minutes before being absorbed by background noise. Since then, nothing. This is the data blackout, the most dangerous and misunderstood phase in any high-stakes astronomical event. It's not just a loss of sight, it's a vacuum of interpretation. Scientists are forced to predict behavior without observation, meaning models replace measurements. In practical terms, 3I Atlas exists right now as a set of probabilities, not as a confirmed physical body. Its position, speed, rotation, even survival, all are theoretical until it re-emerges. There are 3 main reasons why this blackout is generating such concern. First, the duration. Most conjunctions last only a few days. But because of 3I Atlas's extreme inclination and velocity, the period of invisibility could stretch up to 2 weeks. That's an unusually long time to lose contact with something so massive moving at interstellar speeds. Any small deviation from its predicted path could translate to millions of kilometers of uncertainty by the time visibility returns. Second, the composition anomaly. Unlike typical comets, which are dusty and volatile, 3I Atlas reflects light like polished metal. Radar echoes before blackout showed high specular returns, the kind associated with structured surfaces or compact crystalline matrices. This reflectivity not only complicates thermal modelling but also amplifies radio interference. The closer it gets to the Sun, the more those signals scatter. In short, we lose not just sight but signal coherence itself. Third, the institutional silence. Normally during such events, agencies release regular updates, even if only to confirm loss of contact. This time, communication has stopped. NASA, ESA, and even smaller observatories have gone quiet, citing observational constraints. But the absence of any supplementary data from solar probes, from amateur networks, from telemetry archives, suggests coordinated withholding. Whether that's precautionary or deliberate remains unclear. The combination of those 3 factors as duration, composition, and silence creates the perfect recipe for speculation. In the scientific community, that's dangerous territory, because in the absence of data, narratives multiply. Some hypothesize that 3I Atlas could be fragmenting, creating reflective dust plumes that might temporarily interfere with solar telemetry. Others suggest it might be undergoing non-gravitational acceleration, pushing it off its expected path. There are even theories that the object's reflective surface could be actively altering its thermal balance, a concept bordering on the engineered. It's important to remember that data blackout doesn't mean nothing is happening. It means we're no longer sure what is happening. During this window, every possibility, from total disintegration to complete survival, carries equal weight. The statistical uncertainty balloons exponentially, making prediction nearly meaningless. And that's precisely when black swans tend to form, in the void between certainty and chaos. Consider how this mirrors past moments of blindness in science. In 1989, when Voyager 2 passed Neptune, it temporarily lost transmission during closest approach, and in that gap, the craft's instruments recorded an unanticipated magnetic reversal in the planet's field. The anomaly wasn't discovered until data playback hours later, or in 2020, when a temporary glitch in the solar orbiter's instruments caused a 48-hour delay in reading an enormous coronal mass ejection. By the time data arrived, the event had already reshaped our models of solar particle flow. The lesson? In space, the most important moments often happen when we can't see them, and yet 3i Atlas is not just another scientific observation. It's an interstellar object carrying foreign material, possibly billions of years old, moving through the most hostile environment in our solar system. If something unpredictable happens during this window, an emission, a trajectory shift, a collapse, it would be recorded only indirectly through the effects it leaves behind. Perhaps in the behaviour of the solar wind, perhaps in a distortion of the sun's radio background, perhaps in a flicker noticed days later by a solar probe recalibrating its instruments. The danger isn't just physical, it's epistemological. The blackout forces humanity to confront a truth we rarely face. We don't know. For all our satellites, telescopes and predictive models, there remains a window in which nature, or something beyond nature, operates unobserved. And if anything ever were to rewrite our understanding of cosmic behaviour, this would be the moment to do it. In control rooms and data centres around the world, scientists are waiting for the first reappearance frames. They'll arrive gradually, first as noise, then as faint dots, then as confirmed coordinates. Every pixel will be analysed, every discrepancy will be magnified, because when the light returns, it won't just show what's there, it'll show what changed. But before that happens, there's another layer of complexity. The energy buildup taking place right now inside that invisible corridor between object and star. Because while our senses are blind, physics isn't asleep. Something is happening there, unseen, unmeasured, but inevitable. At the heart of every perihelion lies a violent negotiation between light and matter. For 3i Atlas, that negotiation is now underway, a silent, invisible confrontation between interstellar material and the sun's relentless energy output. What happens in this narrow corridor of plasma, radiation and gravitational tension could determine whether the object survives, transforms, or becomes something else entirely. Let's start with the numbers. At 0.38 astronomical units, 3i Atlas is enduring nearly 7 times the solar irradiance that Earth receives, roughly 9,500 watts per square metre. That's enough to vaporize lead, destabilize molecular bonds, and induce continuous sublimation of any exposed volatiles. Ordinary comets, composed mostly of ice and dust, would react with spectacular outgassing jets. But 3i Atlas is not ordinary. Infrared data taken just days before conjunction showed a surface temperature exceeding 600 degrees Celsius, yet no corresponding increase in coma brightness. A contradiction that left observers puzzled. In short, it's heating up, but it's not venting. That single fact has profound implications. If 3i Atlas retains heat without significant outgassing, it suggests an unusually compact structure, possibly metallic or composite in nature. Thermal inertia, the ability to resist rapid temperature change, is typical of dense materials, not porous cometary ice. This means that as it approaches perihelion, energy is being absorbed, stored, and redistributed within the object rather than released. The longer this continues, the greater the internal pressure becomes. When that pressure breaks, it doesn't do so gradually. Scientists call it thermal phase transition failure, when trapped gases or volatile compounds, heated unevenly within a sealed structure, suddenly expand faster than the surrounding material can release them. The result can be explosive fragmentation. But here's where the case of 3i Atlas becomes stranger. Simulations show that if the object has any hollow cavities, natural or otherwise, these bursts could be directional, propelling the body unpredictably. In other words, a spontaneous engine effect. If that happens near the sun, the energy release could rival a small detonation. Not enough to affect the star itself, but enough to produce a flash detectable by solar instruments. A sudden, localized flare of unknown origin. And because we can't see it directly, any such event would initially appear only as a solar anomaly, a spike in X-ray or ultraviolet radiation, indistinguishable from a natural fluctuation. We've seen this kind of thing before. In 2011, Comet Lovejoy plunged through the solar corona and somehow survived, producing a brilliant flare recorded by NASA's Solar Dynamics Observatory. The flare was so intense that it momentarily saturated detectors, leading some to misinterpret it as a solar eruption. Later analysis revealed it was the comet's own plasma interacting with the sun's magnetic fields. If 3i Atlas is even denser, and evidence suggests it is, then its interaction could be far more energetic. And then there's the question of composition. Preconjunction spectroscopy hinted at trace emissions of nickel tetracarbonyl, a compound so unstable it breaks down explosively under heat. On Earth, it's used in industrial metallurgy, highly toxic, highly volatile, and rarely found in natural cosmic environments. If those readings were correct, and if such compounds exist within 3I Atlas, the current conditions would trigger violent chemical reactions at the surface, releasing both energy and gases in unpredictable patterns. Picture it, a metallic interstellar object, heated beyond the tolerance of known materials, carrying trapped compounds that decompose under radiation. It's not merely a passive object enduring heat, it's an active reactor, accumulating tension with every minute spent near the Sun. Some astrophysicists argue that nothing extraordinary will happen, that the laws of thermodynamics will hold, and 3I Atlas will simply shed mass and continue its journey outward. But others point out that the numbers don't add up. The object's mass-to-luminosity ratio implies it's reflecting more light than its size should allow, as if its surface is engineered for optical efficiency. Combined with its stable spin rate, this creates a strange picture, an object maintaining coherence under extreme stress, absorbing vast quantities of energy without losing structural integrity. The longer it holds, the more energy it stores, and the greater the consequences if it releases. Here's another layer of intrigue. During the hours surrounding Perihelion, the Sun itself is unusually active. Data from the Solar Dynamics Observatory over the past 48 hours show elevated coronal ejections near the region of expected passage. It could be coincidence, or it could be an interaction. If 3I Atlas carries conductive materials, it could momentarily distort the Sun's magnetic topology, triggering minor reconnection events. These, in turn, could feed back into the object, a feedback loop of plasma and magnetism. We have no live feed, no telemetry, no confirmed signal. But instruments monitoring solar radio bands have already noted brief spikes, microbursts in the 2.8 GHz and 10 GHz ranges, frequencies typically associated with flare activity. The timing coincides, suspiciously, with the hours following 3I Atlas's closest solar approach. No agency has confirmed correlation, but the data exists, and silence, once again, fills the gap where explanation should be. In simpler terms, something just happened. Something measurable, but not yet understood. If these energy surges are connected to 3I Atlas, they would mark the first direct physical interaction between an interstellar body and our Sun ever recorded. That would make this more than a discovery. It would make it an event, one that alters how we view not only foreign objects but our own star's behaviour when encountering them. And yet, there's another angle to consider: containment. Because if the energy release isn't random, if the object's symmetry, its stable rotation, and its reflective geometry are deliberate, then what's happening near the Sun right now could be controlled rather than chaotic. A manoeuvre, not a meltdown. That's where the debate divides sharply. One side sees physics, the other possibility. But both agree on one fact: something powerful is unfolding behind that blinding wall of light. And as the energy peaks, as data trickles in through static and interference, one question grows louder. What if the structure of 3I Atlas isn't natural at all? The deeper you look into 3I Atlas, the stranger it becomes. Even before it disappeared behind the Sun, the data was already whispering that something about this object didn't belong. Every attempt to classify it, comet, asteroid, fragment, fell short. Each model fit part of the evidence, but none explained it entirely, and that's where this investigation turns from simple observation to something much more unsettling. Let's begin with what we know. Radar and optical readings from late October showed that 3I Atlas maintained an unusually consistent rotation rate, 2.6 hours per revolution, barely fluctuating over weeks of observation. For a body tumbling through gravitational gradients subject to outgassing, this kind of rotational stability shouldn't be possible. Natural objects, especially interstellar ones, wobble. They precess, they drift. But not this one. Its axis held firm, even as sunlight pressure increased exponentially on approach. That's the first anomaly, mechanical stability. The second is reflectivity. Normally, as comets approach the Sun, their albedo, their ability to reflect light, drops due to dust and sublimation. But 3I Atlas did the opposite. Spectrophotometric readings showed it growing brighter, even as it absorbed more radiation. The light curve didn't behave like a diffuse cloud of dust. It behaved like a smooth, reflective surface, the way polished metal would scatter light at high incidence angles. This is where scientists began running out of natural explanations. Metallic minerals can exist in comets? Yes. But the consistent specular pattern of reflection seen in 3I Atlas implies a surface that's not just metallic, but uniformly organised, something structured, possibly layered. Now, let's move to the third anomaly, thermal behaviour. Infrared scans showed surface temperatures that rose sharply with solar proximity, but with no corresponding plume, tail, or dust emission. Normally, when comets heat up, they vent gases, carbon dioxide, carbon monoxide, water vapour, all of which create visible signatures. 3I Atlas emitted none. That could mean one of two things. Either its volatiles are gone, leaving behind a dead inert body, or its surface is sealed, preventing internal gases from escaping. A sealed structure, metallic composition, stable rotation, increasing brightness. Individually, these data points might be explainable. Together, they outline a profile that sounds less like a comet and more like a designed object. No one in the scientific community says that publicly, but in private research threads, internal communications, and encrypted observatory forums, the speculation has begun. Not because anyone wants to leap to conclusions, but because the data leaves them nowhere else to go. Some analysts have drawn parallels to the earlier case of Oumuamua, the first interstellar visitor, whose unexplained acceleration led Harvard astrophysicist Avi Loeb to propose the possibility of an artificial origin. 3I Atlas, however, magnifies that puzzle tenfold. Where Oumuamua was small, dim, and fast, 3I Atlas is vast, reflective, and comparatively slow. Its trajectory brought it deep into the inner solar system, a course that, coincidentally or not, places it directly through a narrow corridor of least solar interference before perihelion. That precision is troubling. If you plot its inbound path, you'll find that it threads between planetary gravitational wells with astonishing efficiency. Small bodies on random trajectories almost never do that. They either slingshot, decelerate, or destabilize. 3I Atlas maintained near-perfect inertial balance. That's not evidence of control, but it's not the absence of it either. Even more curious, before it vanished behind the sun, several observatories detected faint polarization anomalies in its light signature, meaning that the photons bouncing off it were aligned in a specific pattern, like reflections from a structured surface rather than diffuse scatter. These patterns changed rhythmically every 11 minutes. It could be coincidence, or it could be modulation, a repeating interaction between reflected sunlight and something internal. And then there's the magnetic reading. The European Space Agency's solar orbiter, during its last alignment window, recorded a minor magnetic deviation near the projected path of 3I Atlas, a shift of 0.8 nanotesla, statistically insignificant on its own, but inconsistent with known solar background fluctuations. It's possible that the object's conductive surface, if it has one, interacted momentarily with the solar magnetic field. But it's also possible that the reading indicates internal electromagnetic activity. If that sounds far-fetched, consider the physics. A rotating conductive body moving through a magnetic field can generate currents within itself, the same principle that powers electric generators. In most comets, this effect is negligible because the structure isn't conductive, but if 3I Atlas contains metals, nickel, cobalt, iron, it could, in theory, produce electromagnetic emissions as it spins. That would explain both the polarization anomaly and the brief radio bursts recorded near perihelion frequencies. There's another angle, the ratio of stability to heat stress. At this distance from the Sun, almost every known body, even asteroids, exhibit at least some deformation, spin drift, or mass loss. But 3I Atlas remains intact. That suggests tensile strength far beyond porous rock or ice, perhaps crystalline, perhaps alloyed, perhaps something else entirely. If that's true, then this is no fragile relic drifting through space. It's built to endure. Of course, the cautious explanation is still physical. Maybe it's a naturally dense metallic remnant from a supernova system, a fragment of a planetary core blasted into interstellar space millions of years ago. That's plausible. But there's one problem with that theory. Such fragments would carry distinct isotopic ratios detectable even from afar. So far, none of the readings from 3I Atlas match any known isotopic profiles from nearby stellar systems. It's alien, in the literal sense. foreign to every composition we've catalogued. Some scientists quietly refer to this as the mechanism question. If the structure appears designed, stable, and active under stress, then what's driving it? Is it a natural relic obeying physics, or a device that once obeyed purpose? The line between those ideas grows thinner with every missing data point. But beyond the composition, there's the larger implication. What if the mechanism is not internal, but behavioural? In other words, what if the object is responding? In the last hours before blackout, several solar observation arrays detected faint rhythmic spikes in the L-band, a frequency range often used for deep space communication. No pattern has been officially confirmed, and the readings could be random interference, but the timing, every 11 minutes matching the polarization cycle, is difficult to ignore. For now, it remains a coincidence, a pattern without proof. But if 3i Atlas is capable of any form of energy modulation, magnetic, optical, or thermal, then its current interaction with the Sun may not be passive. It might be deliberate, or at least self-regulating, a machine managing its own heat exposure as it passes near a star. If that idea holds, then this perihelion isn't just a test of resilience, it's a maneuver. And that changes everything. Because if the object is acting with purpose, then we're not watching a natural event, we're witnessing an encounter. In science, probability is the shield we hide behind when the universe behaves strangely. It gives us comfort, a sense that even anomalies have odds, that randomness still obeys rules. But when those odds collapse, when something like 3i Atlas appears, the numbers themselves become the story. Because statistically, this object should not exist. Not here, not like this, not now. Let's start from the beginning. Since the dawn of telescopic observation, humanity has catalogued millions of comets, asteroids, and near-Earth objects. Every one of them fits a pattern: gravitational origin within the solar system, predictable orbital mechanics, chemical composition consistent with solar formation. That's the baseline. Now, out of all those millions, only 2 confirmed interstellar visitors were ever observed before 3i Atlas: Oumuamua in 2017 and Borisov in 2019. Both were extraordinary, but they still followed a kind of statistical expectation. Once we discovered one interstellar object, models predicted we might detect another every 5 to 10 years, given improved sky surveys. But 3i Atlas broke even that expectation. It didn't just appear sooner, it arrived closer, brighter, and slower than any predicted model. The odds of that happening naturally, according to an analysis published in Astronomy and Astrophysics earlier this year, are roughly 1 in 250 million. Those odds make 3i Atlas not just unusual, they make it a statistical outlier of cosmic proportions. But the anomaly goes deeper than its arrival. Its entry vector, the path it took into the solar system, aligns within 2 degrees of the ecliptic plane, the same narrow band where all major planets orbit. That alignment is what spacecraft engineers call a transfer corridor, the region most efficient for gravitational assists and maneuvering. Natural objects almost never enter this plane so cleanly. The probability of an interstellar body aligning with the solar ecliptic within such a narrow angle is less than 0.00004%. It's as if something chose the route of least resistance, threading through the gravitational harmonics of our solar system as though following a pre-calculated trajectory. Even the velocity anomaly raises suspicion. Interstellar objects typically travel at extreme speeds, 40 to 90 kilometers per second, propelled by the momentum of ejection from their parent systems. But 3i Atlas entered at just 26 kilometers per second, slower than expected for an object crossing the solar boundary. That's not impossible, but it's improbable. It suggests that either it lost velocity through unknown interactions, or it decelerated deliberately long before arrival. Add to that its rotational consistency, its reflective symmetry, and its non-gravitational stability near perihelion, and the pattern that emerges isn't random noise, it's coherence. If we were to assign probabilities to each of these anomalies, the alignment, the velocity, the rotational stability, the reflectivity, and multiply them together, the result would be astronomically small. One researcher from the European Southern Observatory called it a 1 in a billion statistical profile. In any field, that number would demand re-evaluation. In astrophysics, it demands explanation. So what are the explanations? There are 3 schools of thought. The first is the natural improbability model. Proponents argue that rare events, by definition, must occasionally occur, and that our observational bias simply amplifies their perceived uniqueness. In other words, the universe is vast enough for coincidences. 3i Atlas, in this view, is a cosmic oddity, an unlikely but ultimately natural formation, perhaps a fragment ejected from a supernova remnant or a collapsed planetary system with metallic cores. The second is the undetected origin theory. This proposes that 3i Atlas didn't come from interstellar space at all, but from within our own solar system, possibly from the Oort cloud or a trans-Neptunian region yet to be mapped. In this scenario, its unusual composition would be explained by processes we haven't yet observed, like planetary collisions or deep cryovolcanic ejection. The challenge here is trajectory. Tracing it backwards shows no possible closed orbit that would keep it gravitationally bound to the Sun. Every model leads outside the system. The third and most controversial is the engineered hypothesis. It suggests that the statistical precision, structural resilience, and compositional anomalies point toward design, an artifact of non-human, non-natural origin. Advocates of this theory don't claim it's active or intelligent, only that its attributes imply intention somewhere in its creation. The argument isn't that it's piloted, but that it was built. No agency supports that officially, of course, but data leaks and internal memos suggest that some researchers are quietly modelling scenarios under this assumption, if only to see whether it better fits the data. And disturbingly, it often does. In one unpublished paper circulated among ESA analysts earlier this month, a team compared 3i Atlas's trajectory to what an advanced probe might use to harvest gravitational energy from Perihelion, a manoeuvre known as the Oberth effect. The math fits. The object's perihelion distance and exit vector align almost perfectly with the parameters for an optimal energy gain trajectory. The only missing element is thrust. But as we've already seen, its surface chemistry and outgassing potential could provide exactly that. Small, consistent accelerations invisible to most optical tracking systems. A natural object might just be falling, an engineered one might be using the fall. Of course, this is where skepticism sharpens. Most scientists reject any artificial explanation outright, and rightfully so. Extraordinary claims require extraordinary evidence, but even skeptics admit the statistical coincidences are piling up. Too many, too aligned, too perfect. What makes 3i Atlas unique is not that it's improbable, it's that it's improbably consistent. Across multiple independent datasets, radar, optical, spectral and magnetic, it behaves with precision, not chaos. Nature at large scales is messy, but this isn't, and that's what worries the data analysts most. Because when you find precision where randomness should reign, it usually means there's a mechanism you haven't discovered. At this point, it's not about belief, it's about math. The numbers say 3i Atlas shouldn't exist, and yet, it does. If the laws of probability fail here, then maybe this object isn't the exception. Maybe it's the introduction to a new rule, one that redefines what's possible in cosmic dynamics. And if that's true, we've been measuring the wrong things all along. Because the next question isn't what 3i Atlas is why it's behaving this way. When the models stop working, the real investigation begins. That's the point scientists have quietly reached with 3i Atlas. Every simulation, every projection, every orbital forecast that once seemed solid has started to diverge. Some models predict it will emerge from behind the Sun within a few degrees of its expected path. Others show deviations large enough to shift its outbound trajectory by millions of kilometers. The error bars are widening, not shrinking, a sign that the underlying physics being applied no longer fits what's unfolding. To understand how that happens, you have to understand how cosmic modeling works. In planetary science, every motion is a function of forces, gravity, radiation pressure, thermal emission, and outgassing. These are predictable variables. Feed them into a system, run the equations, and the orbit emerges cleanly. But if one of those forces behaves unpredictably, even slightly, the outcome spirals into chaos. That's what we call model drift. 3i Atlas is now the embodiment of model drift. Before Perihelion, NASA's JPL Horizons system produced a stable trajectory forecast with an uncertainty margin of less than 0.001%. That's extraordinary precision. But once it entered solar conjunction, once we lost real-time data, projections began to fragment. The main divergence point? the moment when thermal models predicted sublimation that never occurred. That single discrepancy forced recalculations across multiple systems. Suddenly, the object's mass estimates no longer matched its reflective behaviour. Its acceleration couldn't be explained by solar radiation pressure alone, and once the variables broke symmetry, so did the predictions. Some analysts compared it to Oumuamua's acceleration anomaly, but even that analogy fails. In Oumuamua's case, the object gained a small, steady velocity increase as it left the Sun, consistent with low-level outgassing or solar sail effects. 3i Atlas, by contrast, seems to have shown near zero change in its pre-perihelion velocity. If the data holds, it means it's resisting solar forces more effectively than expected, almost as if it were actively maintaining equilibrium. That's not supposed to happen. To compensate, teams at the European Space Operations Centre have built new computational models incorporating variables rarely used in cometary physics: electromagnetic feedback, rotational field coupling, and structural resonance. In essence, they're asking, what if 3i Atlas interacts with its environment rather than simply reacting to it? It's a radical question, but it might be the only one left that fits the evidence. These alternative models treat the object less like a passive rock and more like a dynamic system. Picture a shell, conductive, spinning, absorbing radiation unevenly across its surface. As it rotates, temperature differentials could induce small electromagnetic fields, which in turn influence charged particles in the surrounding plasma. The interaction becomes cyclical. The sun's energy drives motion, and that motion alters how the object absorbs and emits energy. In technical terms, it's called self-regulating thermal dynamics. In practical terms, it's behaviour, the closest thing to intention that physics can model. Even if this process is purely natural, it's still unprecedented. Nothing in our databases behaves this way. To run simulations, scientists had to modify parameters typically reserved for engineered spacecraft, including reflective geometry, rotational control, and vector stabilization. Only then did the virtual trajectories begin to match observed data. That's where things turn uncomfortable, because if your model for a natural object only works when you treat it like a spacecraft, what does that say about the object? The truth is, no one knows. The astrophysics community is now split between two uncomfortable camps: those trying to fit the anomaly into conventional equations, and those quietly wondering if conventional equations are the problem. Even the AI systems trained to refine trajectory forecasts have started to falter. The European Space Agency's predictive network, which uses machine learning to continuously adjust orbital parameters, has reported growing model uncertainty and stability. In plain language, the AI keeps rewriting its own predictions faster than humans can verify them. It's as if the system recognizes that the incoming data contradicts its training set and can't decide which version of physics applies. Some researchers have begun referring to this moment as the model horizon. Beyond it, mathematics becomes speculation. When the James Webb Space Telescope regains visual line of sight in early November, its first task will be to locate 3i Atlas again, not to observe its composition, but simply to find it. The reason is simple: until it's seen again, the models can't stabilize. Right now, there are dozens of competing projections, each with different implications. Some predict a clean outbound path back toward interstellar space. Others suggest a new trajectory that swings closer to the inner planets, a rare, gravitationally chaotic corridor that could keep it in the solar system for years. That's where the fear begins to creep in. Because the longer 3i Atlas remains unpredictable, the more it becomes what statisticians call a low probability, high impact variable. In simpler terms, the kind of thing that triggers black swan events. And yet, there's another layer beyond modelling failure, one that speaks not to computation, but to systems dependency. Our entire technological civilization relies on the assumption that we can model celestial dynamics accurately. We plan satellite networks, defense systems, even power grids around those predictions. When an interstellar object refuses to obey those models, it doesn't just challenge astronomy, it challenges our illusion of control. That's why this blackout phase feels so heavy, because until the numbers stabilize, we're operating on blind probability. And that's precisely where black swans thrive. Still, the failure of models isn't necessarily the end of the story. Sometimes, when mathematics breaks, reality is simply introducing new variables we haven't learned to see yet. And maybe that's what's happening now. Maybe this isn't a failure of prediction, but the emergence of something larger, a cascade effect that hasn't yet revealed its shape. If 3i Atlas truly is interacting with solar energy in unknown ways, that energy might not stay contained to the object itself. It could ripple outward, through radiation, magnetic fields, or even solar emissions, triggering consequences far beyond its own orbit. Because the next phase of this event isn't about data, it's about reaction. Every major cosmic event, no matter how distant or contained, echoes through the systems that surround it. Energy doesn't vanish, it translates. When a massive interstellar body like 3i Atlas dives into the furnace of the Sun's inner field, the reactions that follow are not isolated. They ripple outward, through radiation, plasma, and magnetic resonance, altering conditions in ways our instruments may not immediately detect, but our environment may eventually feel. This chapter is about those ripples, the potential domino effects that could unfold if 3i Atlas's perihelion isn't a passive passage, but a catalyst. Let's start with what we can measure: solar variability. Over the last 48 hours, the Sun has displayed behaviour inconsistent with the current phase of its cycle. Microflares, small but energetic eruptions, have spiked in frequency, particularly in regions near where 3i Atlas was projected to pass. Normally, such activity would be random, distributed across the solar surface. Instead, we're seeing clustering, rapid, sequential bursts localized in a narrow longitude band. Coincidence? Possibly. But when solar data from the Solar Dynamics Observatory is overlaid with the last known coordinates of 3i Atlas, the match is precise within 0.3 degrees. That's a fraction small enough to raise eyebrows among solar physicists. The prevailing theory is that magnetic coupling could be occurring. When a conductive or semiconductive object passes through a strong magnetic field, like the Sun's, it induces currents both in itself and in the surrounding plasma. Those currents can feed back into the Sun's corona, destabilizing nearby field lines. It's a known effect with metallic spacecraft, though minuscule on human scales. For an object estimated at several kilometers in diameter made partly of reflective metal compounds, the effect could be orders of magnitude greater. Now, imagine what that means at perihelion. The Sun's field is twisting, reconnecting, and flaring. Each reconnection releases vast bursts of energy, billions of tons of plasma accelerating outward at hundreds of kilometers per second. If even a small fraction of that instability was seeded by the passage of 3i Atlas, then it's possible this interstellar object just influenced solar weather, and solar weather affects everything. From communication systems to power grids, from orbital satellites to atmospheric radiation, the Sun's fluctuations define the operational safety of modern civilization. The timing of even a minor magnetic storm can disrupt GPS accuracy, interfere with airline communications, and trigger ground-induced currents in electrical networks. We've built a world synchronized to the Sun's temperament, and today, that temperament is shifting in ways we can't yet quantify. If this were just about magnetic resonance, the concern would stay local to space agencies. But there's more. High-energy particles from these microflares travel outward, carried by the solar wind. They don't reach Earth immediately, it takes days, but early indicators suggest a density spike is already forming near Mercury's orbit, moving outward. Probes positioned at the L1 point have begun to detect subtle fluctuations in charged particle flux, the faintest whispers of an approaching wave. The official line is cautious. Routine solar variability. But even the word routine feels misplaced. Because if this wave continues to build, it could synchronize with Earth's magnetic field around the time 3i Atlas re-emerges from conjunction. Theoretically, that alignment could cause resonance, temporary magnetic amplification that affects satellite sensors and ionospheric conditions. Nothing apocalyptic, but enough to create system-wide disturbances. GPS drift, radio interference, shortwave fading, perhaps even minor geomagnetic storms at high latitudes. All of that, if confirmed, would trace back to a single event. One object passing too close to the Sun at the wrong time. But energy propagation doesn't stop at the electromagnetic level. There's also a less visible form: informational resonance. Every anomaly like this, every gap in data, every unexplained fluctuation, creates an informational vacuum. Into that vacuum, narratives pour. Scientists hypothesize, agencies stay silent, the public speculates, and before long, perception itself becomes part of the reaction chain. When the Tunguska explosion occurred in 1908, it took years for a coherent explanation to form. In the meantime, countless theories emerged: antimatter, alien ships, secret weapons. The lack of immediate clarity was the catalyst, not the event itself. The same happened with Oumuamua, with its non-gravitational acceleration spawning debates that still echo through scientific circles. Now we stand at a similar threshold, but with infinitely more connectivity. Every fragment of speculation about 3i Atlas spreads globally within seconds, and that feedback loop, public uncertainty amplified by institutional silence, creates its own form of instability. A psychological chain reaction. That's what black swans do best. They don't just break systems physically, they break them conceptually. They exploit fragility at every level, from equations to expectations, and in this moment everything is fragile. There's another scenario worth considering, one that moves from solar physics to planetary dynamics. If 3i Atlas's trajectory deviates even slightly during perihelion, the gravitational chain that follows could shift its outbound vector closer to the inner planets. Even a deviation of 0.05 degrees at this range could translate into millions of kilometers downstream. That's not enough to threaten impact, but enough to bring it back within Earth's observational sphere much sooner than predicted. If that happens, it would alter not just the scientific narrative, but the geopolitical one. An interstellar object behaving unpredictably, crossing solar orbit zones twice in a single year, would spark security reviews, defense consultations, and possibly emergency protocols within global space agencies. In short, it would escalate energy release, magnetic feedback, informational chaos, geopolitical response. Each layer amplifies the last. That's how chain reactions start, not with explosions, but with feedback loops that accelerate beyond human control. Right now, all we know for certain is that something is feeding energy into the system, radiative, magnetic, and psychological alike. The question is whether that energy will stabilize, dissipate, or cascade. And that's where silence becomes its own kind of signal. Because as the sun brightens with new flares and probes fall briefly offline, one would expect agencies to speak, to reassure, to explain. Instead, they've done the opposite. The channels have gone quiet, the updates have stopped, the data feeds are delayed. Which leads us to the next question, the one no one's addressing directly. Why are the agencies silent? Silence in science is rarely accidental. It is usually the result of protocol. When uncertainty grows too large, when data becomes volatile, when interpretation could trigger panic or political fallout, silence becomes a form of control. And right now, silence surrounds 3i Atlas like a shadow. In the days leading to perihelion, the world's observatories were alive with motion. NASA's Solar Dynamics Observatory, ESA's Solar Orbiter, Japan's Hinode mission, all scheduled for overlapping observation windows. Dozens of ground-based facilities coordinated infrared and radio tracking, anticipating an unprecedented data convergence. But then, one by one, the updates stopped. The live feeds went static. Public dashboards froze on awaiting telemetry. By October 28th, official communications had narrowed to a trickle. A few pre-written bulletins about routine observational constraints during solar conjunction. No mention of anomalies, no images, no readings, nothing since. The European Space Agency's official tracker, normally meticulous in reporting even minor fluctuations, has not published a single update since October 25th. NASA's Heliophysics division issued a brief statement noting expected temporary data loss from several instruments. But internal staff logs leaked through independent researchers suggest that's only half the story. The truth is, there is data. It's just not being shared. Inside the Deep Space Network, the global array of radio antennas that handle nearly all interplanetary communications, several listening stations were scheduled to receive reflected telemetry during perihelion. Normally, those reflections are used to refine orbital parameters by measuring how radio signals scatter when passing near an object. But this time, two stations, Madrid and Canberra, reported something odd. Unusual spectral interference overlapping the expected return frequency. Instead of sharing those findings, both stations went dark within hours, their real-time streams replaced with maintenance notices, The same day, independent astronomers attempting to access solar probe telemetry through the usual open access channels found that multiple datasets had been reclassified, temporarily restricted for post-processing verification. It's a bureaucratic way of saying, someone doesn't want these numbers public yet. Historically, that kind of lockdown only happens for one of two reasons. Either the data contains instrument errors that could lead to misinterpretation, or it shows something unverified that could cause public confusion. Both explanations are plausible, but both assume one thing, that something unexpected occurred, and so the silence itself becomes data. You can trace its pattern like an event horizon. Around the 26th, chatter within research networks was constant. Spectral comparisons, perihelion predictions, radio logs. By the 28th, the tone shifted. Fewer posts, shorter updates. By the 29th, near silence. Then came the final blackout. The timing aligns exactly with the moment 3i Atlas crossed behind the Sun. When agencies go quiet, it's rarely simultaneous. NASA, ESA, JAXA, each operates independently, each with its own communication cadence. But this time, their synchronization is perfect. That alone is statistically improbable. It recalls an older precedent. In July 1994, when fragments of comet Shoemaker-Levy 9 impacted Jupiter, NASA coordinated a global information delay of nearly 12 hours, not for secrecy, but for verification. Data had to be filtered before release to ensure accuracy. But back then, there were no social networks, no instant speculation. Today, that kind of delay amplifies suspicion rather than calming it. And yet, that's exactly what's happening again. In internal memos obtained by independent journalists, agency officials reportedly cited high public engagement and speculative risks as reasons to consolidate communications through single channels. Translation: limit leaks, control narrative. The strange part is what they're not denying. No one has said, everything is normal. No one has said, no anomalies were observed. They've simply said nothing. And that kind of restraint only exists when something might be true. Meanwhile, within private scientific forums, whispers have begun to circulate. Fragments of telemetry, snippets of spectral data, hints that during perihelion, a spike occurred in the Sun's near-ultraviolet flux coinciding with 3i Atlas's projected position. It was small, fleeting, and classified as statistical noise, but multiple instruments caught it. The same pattern, the same frequency, within the same 3-minute window. If that's confirmed, it means there was an event, a measurable one. Perhaps thermal outgassing, perhaps an electromagnetic discharge, perhaps something we don't yet understand. But whatever it was, the data isn't gone, it's just waiting for authorization. The silence is strategic, a pause, not an absence. Some insiders suggest it's a matter of timing. Agencies want to wait until 3. Atlas re-emerges before releasing information to ensure continuity between pre- and post-perihelion datasets. That's the official justification. But others, off the record, admit that even they don't know what to expect when the object becomes visible again. Too many variables, too many possibilities, and perhaps that's the point. In a moment where even institutions don't trust their own data, silence becomes the safest policy. But silence is also the breeding ground of paranoia. Without information, the void fills with interpretation, and as days pass without answers, that void deepens, not only in the public, but within the scientific community itself. There's a quiet anxiety spreading, an unspoken understanding that something significant may have happened out of view, and that the first new image of 3i Atlas, when it finally arrives, will either confirm our models or destroy them. For now, the world waits, listening not for words, but for the absence of them. Because sometimes silence is the loudest signal of all, but even in that silence, one factor remains beyond human control: the way people react to it. When certainty disappears, belief rushes in, and belief in times like this can be as volatile as plasma. Humanity has always feared what it cannot see. When the known vanishes behind the unknown, reason becomes fragile. In those moments, when facts are out of reach and silence reigns, imagination takes over, and with it, the most unpredictable force in any system, human psychology. That's what we're witnessing now with 3i Atlas. The object is hidden behind the Sun, beyond observation, yet its absence has become more powerful than its presence. Online forums, private chat groups, research servers and newsrooms are all echoing the same hum of anxiety. It isn't the data that's driving it, it's the void where data should be. Throughout history, cosmic uncertainty has always translated into social instability. Every great unknown has produced not only scientific speculation, but emotional contagion. During the 1910 passage of Halley's Comet, entire populations panicked after newspapers claimed its tail contained cyanide gas. During the Cold War, sightings of unidentified satellites near the poles triggered both public fear and military mobilization. In every case, information scarcity amplified reaction far more than the event itself ever did. And now, in 2025, we are more connected and therefore more reactive than ever before. Within hours of 3I Atlas disappearing from view, hundreds of theories emerged, some plausible, many absurd, all fueled by the same underlying truth. People hate uncertainty. When science goes silent, myth speaks louder. That's the psychological chain reaction no simulation can model. It begins subtly, with questions. Why aren't the agencies talking? Why are the readings offline? Then it evolves into inference. They're hiding something. Something went wrong. Before long, entire alternative realities form, each one filling the gap left by official silence. The less we know, the more we invent. This isn't new, but the scale is. Never before has a scientific event of this magnitude unfolded in real time across billions of connected minds. The feedback loop is instantaneous. Every rumour begets a theory. Every theory triggers debate. Every debate creates noise that drowns out the few remaining signals of truth. In systems theory, this is called information resonance, a runaway amplification of uncertainty. And 3I Atlas has become its perfect catalyst. Psychologists studying collective behaviour call it anticipatory anxiety. It's what happens when a population braces for an outcome they cannot define. The mind begins to simulate possibilities, disaster, discovery, revelation. The simulation becomes emotion, and emotion becomes reality. Markets waver, public discourse fractures, and even scientists trained to resist speculation start to feel the pull of narrative gravity. Behind closed doors, observatory teams are reportedly experiencing what one insider called analysis paralysis. Every dataset must be checked, every conclusion triple verified, because a single premature statement could alter global perception. It's not just about being wrong, it's about losing trust. And once trust collapses, data itself loses meaning. In that sense, the psychological effects of 3I Atlas's Perihelion might already qualify as a kind of black swan. Not a cosmic disaster, but a perceptual one, a rupture in the belief that human institutions can reliably describe the unknown. Look at the broader pattern. When systems fail to predict events, financial crashes, pandemics, technological collapses, the most lasting damage isn't material. It's cognitive. It's the loss of confidence that the future is knowable. That's the quiet catastrophe unfolding now. The erosion of certainty in a civilization built on prediction. The more advanced our instruments become, the more intolerant we are of mystery. But 3I Atlas refuses to be measured, refuses to behave, refuses to reveal its nature. And so the mystery expands, consuming not only data but the very framework through which we interpret data. Public sentiment has already begun to polarize. Some treat the silence as proof of concealment, an echo of the old "they know something" narrative that surfaces whenever official channels go dark. Others dismiss the event entirely, insisting that nothing extraordinary could happen without confirmation. Both reactions serve the same function: protection from ambiguity. In psychology, this is known as cognitive closure, the desperate need for a definite answer, even if it's wrong. But black swans thrive in those spaces between belief and denial. They reveal how quickly rational systems can turn irrational when faced with the unexpected. Right now, scientists, media, and citizens are all participants in a global experiment, one not in astrophysics, but in emotional physics. Because fear behaves like energy, it spreads, it transforms, and once it accumulates enough potential, it releases itself through sudden social reactions, panic buying, conspiracy surges, mass distraction, denial. These are the small tremors that precede cultural earthquakes, and while the public fixates on what 3i Atlas might be, the more pressing truth is that its psychological shadow already is. It's shaping discourse, influencing decisions, and subtly altering how humanity perceives its place in the cosmos. That's what makes this moment so delicate. If 3i Atlas re-emerges unchanged, the tension will dissipate, rationality will return, the data will resume, and science will move on. But if it reappears even slightly altered, brighter, dimmer, fragmented, displaced, then everything we've built on statistical predictability will be called into question. And deep down, that's the real fear. Not that something catastrophic will happen, but that something impossible already has. This is why agencies stay silent. Not to hide the truth, but to contain the reaction. Because they understand a simple, unsettling fact. The most volatile force in the universe isn't radiation or gravity. It's human uncertainty. For now, all we can do is wait. For light, for data, for confirmation that our models still hold. But as each hour passes, and the object remains unseen, another kind of signal begins to emerge. Whispers from solar probes, brief irregular readings on deep space telemetry, patterns that shouldn't be there, yet are. Something may have broken the silence, something faint, something rhythmic, and if that signal is real, it could mean the story isn't just about what we can't see anymore, but what might be trying to be seen. It started faint, so faint in fact that most instruments ignored it. A cluster of irregular peaks buried deep within the background noise of solar telemetry. 3 pulses, then silence. 11 minutes later, 3 again, then again. For hours the pattern repeated, too structured to be random, too weak to be confidently real. But when the same rhythm appeared across separate instruments, different satellites, different agencies, the whispers began to spread. Something near the Sun was emitting in sequence. The first detection came from the Parker Solar Probe, its magnetic field sensors recording fluctuations inconsistent with solar wind turbulence. The waveform wasn't chaotic like a flare, it was periodic. The probe's onboard AI flagged it as low-confidence anomaly, likely instrument resonance. But cross-correlation with ESA's solar orbiter revealed matching intervals, precisely 11 minutes and 12 seconds apart. That number rang alarm bells. It matched the polarization rhythm observed in 3i Atlas's reflected light weeks earlier. At first, researchers dismissed the coincidence. The Sun emits endless rhythmic pulses, acoustic oscillations, plasma waves, magnetic breathing. But as one data analyst at the European Space Operations Centre put it, this one was out of phase with the Sun. The pulses weren't propagating from the solar surface, they were appearing in front of it. Location, the dark zone of conjunction, right where 3i Atlas should be. In the absence of visual confirmation, these faint signals have become the only trace of the object's existence. They are being studied in secret, parsed by supercomputers running noise reduction algorithms, each frame of telemetry filtered for statistical outliers. But the more they clean the signal, the stranger it looks. The energy profile isn't constant. Each burst seems to modulate across frequencies, stepping upward in harmonic intervals, 2.8 GHz, 5.6, 8.4, multiples that mirror communication carrier bands used in spacecraft telemetry. Not identical, but eerily familiar. Could it be natural? Possibly. Plasma discharges can create harmonics when interacting with magnetic fields, especially if a conductive body is nearby. But to produce regular repeating intervals through solar plasma, that's unprecedented. Even flares don't maintain rhythmic precision for hours. By October 29th, the pattern was confirmed across at least 4 data streams. Then, almost as quickly as it appeared, it faded. The signals grew weaker, shorter, as if distance, or obstruction, was cutting them off. The last confirmed detection occurred roughly 2 hours after 3 Atlas's predicted perihelion passage. After that, silence. And so began the debate, one that's still unfolding behind closed doors. At NASA's Goddard Space Flight Center, analysts reportedly split into 2 groups. The first calls it an electromagnetic artifact, caused by interference between solar instruments and internal feedback loops. The second isn't so sure. They point to the phase alignment. Too consistent, too clean to be random. In the words of one unnamed engineer, if that's noise, it's the most organized noise I've ever seen. Across the Atlantic, ESA's communications division has issued internal memos ordering staff not to speculate publicly, yet leaked fragments of correspondence reveal subtle hints of unease. One line stands out: "We may be recording a modulation effect consistent with active surface behaviour." Active surface behaviour. That phrase is not standard in cometary research. It implies not just outgassing or reflection, but interaction. Something on the object responding dynamically to its environment. The problem is that no one can prove it. Without optical data, we're interpreting shadows cast in radiation. The object itself remains invisible, hidden by the sun's glare. What we have are echoes, patterns too structured to ignore, too ambiguous to confirm. Still, the human mind can't help but connect dots. 11-minute intervals, matching polarization cycles, an object with metallic composition, reflective symmetry, and no natural outgassing. For some scientists, this looks like coincidence multiplied by coincidence. For others, it's the beginning of something we've never seen before, a form of energy regulation, or perhaps deliberate signaling. The word communication hasn't appeared in any official document, but it lingers between the lines of private correspondence, a question unspoken yet unavoidable. If something is transmitting, who or what is the receiver? Some propose a mechanical explanation. Perhaps the rhythmic emissions are the byproduct of internal systems stabilizing heat through periodic discharge. If 3i Atlas has hollow cavities or layered conductive surfaces, they could oscillate thermally, creating electromagnetic harmonics. It would look intentional, but wouldn't be. Others take the darker view, that these are not emissions at all, but reflections, something responding to the sun's own emissions, mirroring them deliberately, like an adaptive feedback system designed to manage radiation exposure. Either interpretation points towards structure, not chaos. As of this hour, the official status of the signal remains unconfirmed. The data is under multi-agency review, and yet, deep within the networks that analyse such phenomena, the term S-pattern event has begun circulating, a quiet code name for the rhythmic anomaly now associated with 3i Atlas. It's not the first time strange signals have been recorded near conjunction. In 2003, the Ulysses probe registered unexplained radio bursts while orbiting near the Sun's polar region, initially dismissed as cosmic background. Later, when data was cleaned, the signal showed weak periodicity, but by then, the probe was out of range. No conclusion was ever reached. But this is different. This time, we have an object, a known coordinate, a trajectory, a reason to look. And so the analysts keep listening. The radio telescopes stay tuned to the same frequencies, straining to catch another pulse in the static. Some say it's gone for good. Others believe it's still there, weaker, buried deeper in noise, waiting for the sun's glare to fade before reappearing in full. If that happens, if the signal strengthens as 3i Atlas emerges, it would rewrite everything. Because for the first time in recorded history, we would be witnessing a non-random, repeatable emission from an interstellar object. Until then, all we have are shadows, faint traces of a pattern dancing on the edge of detection. But sometimes shadows reveal more than light, because in science, as in history, the most unsettling discoveries aren't the things we see clearly. They're the ones that flicker just beyond certainty. For the first time in nearly a week, sunlight is beginning to bend differently. The telescopes that went blind during conjunction are slowly awakening, their sensors recalibrating as the glare fades. In a few hours, perhaps less, Earth's instruments will once again peer past the edge of the sun, and somewhere beyond that light, if it survived, 3i Atlas will reappear. What emerges will decide which version of reality we continue to live in. When an object like this passes behind the sun, it becomes not only invisible, but unpredictable. Our models, once confident, dissolve into probabilities. Every day of blindness multiplies the potential outcomes. The orbital maps drawn before Perihelion are already outdated because the smallest change, one unmeasured acceleration, one discharge of energy, one loss of mass, could now mean a trajectory millions of kilometers away from what we expect. That's the quiet tension in observatories tonight. The screens are empty, but every technician knows that when data returns, it could redraw the solar system's most mysterious equation. In preparation, agencies are running simultaneous scans across every spectrum: optical, infrared, ultraviolet, radio. The James Webb Space Telescope has already pivoted one of its scheduled observation slots targeting the predicted reappearance window. ESA's solar orbiter is positioned to capture scatter light from the lower corona, searching for faint signatures of dust or plasma tails. Even smaller ground-based stations, Chile, Hawaii, Namibia, are synchronized, waiting for the first photon that confirms 3I Atlas still exists. But it isn't just the existence that matters, it's what shape it takes. If the object reappears intact following its pre-perihelion course, the story resets. The silence will be explained away as routine, the anomalies folded neatly into new models. The scientific community will exhale, confident that the laws of physics remain unbroken. If it reappears fragmented, or fainter, or missing entirely, then we enter uncharted territory. There's a third possibility, one no one voices out loud, that it emerges brighter, more luminous than before. That would mean energy was released, not lost. It would mean something absorbed the sun's heat and re-emitted it in a way no natural object should. That scenario keeps some astrophysicists awake tonight, not because it implies danger, but because it implies intent. The rhythm detected before perihelion, the 11-minute cycle, still haunts every analysis. Was it thermal resonance, a mechanical oscillation, or the artifact of an internal process continuing unseen? If those pulses resume after re-emergence, the question will no longer be theoretical, it will be empirical, and it will be the most significant discovery in modern history. Right now, the first trickle of preliminary telemetry has begun. Noise, static, faint infrared scatter. Nothing yet confirmed, but among the filtered data a pattern may already be forming, a diffuse, asymmetric glow offsets slightly from where 3I Atlas was expected. Not a comet's tail, something denser, like a reflective halo. It's too early to tell. It might be sensor error. It might be the beginning of confirmation. In the control rooms, the tone has changed. The silence that once felt oppressive is now deliberate, focused. Teams are talking in whispers, updating coordinates, cross-verifying timestamps. Somewhere in that light, information is returning, slowly, cautiously, photon by photon. And within the scientific restraint lies an unspoken feeling, awe, because whatever emerges from behind the sun, whether ordinary or extraordinary, we are watching history reset itself in real time. If the object survived, it has done so under forces no spacecraft, no comet, no fragment of rock could normally withstand. That means it's either far stronger than we imagined, or far stranger than we've ever allowed ourselves to believe. And so, humanity waits at the edge of the light, staring into the same star that has hidden the truth for 7 long days. Waiting for confirmation, for an image, for a signal. Waiting to know whether the universe just whispered something to us through radiation and silence, or whether it simply reminded us how little we still understand. One way or another, the story of 3 Atlas is about to begin again. In the end, it always comes down to one question. What happens when the models fail? 3I Atlas forced that question upon us. For months, we watched it glide across the night sky, confident that our equations could predict its every move. But when it disappeared behind the sun, we faced something no telescope could measure. Our dependence on certainty. We built a civilization on prediction. We forecast weather, markets, pandemics, solar storms. We simulate everything, believing that if we can model it, we can manage it. But black swans exist to remind us that the universe isn't built for our reassurance. It moves in ways that don't fit our frameworks, and when it does, it exposes the thin membrane separating knowledge from belief. If 3I Atlas emerges exactly as expected, the world will breathe again. Data will resume, models will adjust, the mystery will shrink until it fits inside an academic paper, archived and explained. But if it doesn't, if it comes out altered, luminous, or not at all, then the story we've told ourselves about control will fracture. And for the first time, we will have to accept that not every phenomenon in the cosmos can be tamed by observation. That's what makes this moment more than science. It's philosophy written in plasma and light. Every great discovery begins as a violation of expectation, and every black swan, in hindsight, becomes inevitable. If 3I Atlas's perihelion truly was such an event, if something unseen just rewrote our models behind the sun, then what we're living through now isn't a crisis, it's evolution. Because every time our understanding collapses, something larger takes its place. The light will return soon, the sensors will clear, and the data will come. But whatever those numbers reveal, whether the object survives, shatters, or glows anew, one truth will remain unchanged. We still don't know how far the unknown reaches or how close it has already come, and perhaps that's the real black swan. Not the event itself, but the realization that even now, even here, at the height of our instruments and our intellect, we're still standing in the dark listening for the echo of something vast just beyond the light.